Okay, so we looked at closed loop. What are the different control techniques? And this was your voltage mode control, where your duty cycle is controlled by the V control generated by your compensator. So we look into more detail about the control loop later. Let's first look into the different types of losses which are in your switching converter. Okay, so PWM and PWM bar are known so they are inverting but non-overlapped. So what could be the different types of losses here? So this is your switching. So since this is a PMOS, we want to invert it. So when PWM is high, this will be on, and when PWM is high, this will be low. So this will be low. Sorry. Okay. So this is your RDCR, and this is your ROP. So number one, conduction loss. Nothing but I of RMS square into R. So whatever the resistive losses are, you can also call. And resistive losses are defined by I square R. So whatever the RMS current, so in the conduction path, so this is your current path. So when PMOS is conducting, it's going through R on P and RDCR and goes into the load. Okay. And we already talked about this. What was the total loss? I load square. So RMS is pretty close to, if your ripple current is very low, then you can ignore. So your basically RMS will be same as your load current. But if your ripple is large, then you cannot assume I load, but you'll have to take into account the ripple as well. So if I call it IL, then better to write IL rather than I load. Okay, so where IL will have a average will be a load current plus you'll have a ripple on top of this. Okay. Multiplied by what do you have R? So you have a D times plus 1 minus D plus R. Okay, that's how you, if you know the duty cycle, you can calculate the RMS losses. Okay. And RDCR is usually specified by the type of inductor you are using. So if you look at the data sheet, it will tell you RDCR number, and R on P, R on N comes from the design. So depending upon how much conduction losses you can afford, that you have to design your power fed according to that, or size your power fed according to that. So you have to budget your losses first. So let's say your target is 90% efficiency, which means total loss you can afford 10% of the power you are delivering. So let's say I deliver a 1 watt, so which means 100 milliwatt roughly you can afford to lose in the power stage, and according to that, then, but this is not the only loss, you have a switching losses also. So but at high current, this is the most dominant. Okay, so 100 milliwatt, which means 1 amp is the total current, and if you consider your RMS is roughly same as your load current, so for 1 amp current, what should be the resistance? 100 milliohm. Okay, so that 100 milliohm should be split into RDCR and R on P, R on N. Okay, and if you keep them same, let's say R on P, R on N, then you can split 50 milliohm, something like that. Okay, each. So then you have to choose the inductor properly to make sure that RDCR should not increase that, otherwise your efficiency will be less than 90%. And you have to size your NMOS and PMOS according to that. So conduction loss, what could be the other loss? So let's say this has a gate. CP, C, and this is a period of TS. So what is the loss due to this switching? The gate. So gate switching loss, I call it E gate system. CP, what is B? VDD square, and F is nothing but what? I'll call it FSW, and FSW is nothing but 1 over plus you have two gates. How much will be that? Cn. So nothing but Cp plus Cn. Okay. So this is not a function of load current. So if you look at a conduction loss, what would happen at light load? So let's say your IL approaches 0, your conduction losses will be 0. But if you are still switching, this will not change. So this remains fixed. These are fixed losses actually. For constant VDD and FSW. Okay. So if your FSW supply voltage is not changing, then this loss will remain fixed. So let's take an example. So let's say your Cp equal to Cn equal to 10 picofarad. Okay. So this is hypothetical number, but when you size it, then you will know what exactly the number will come. But usually it comes order of 5/10 of picofarad, depending upon, for if your size is for 50 to 100 milliohms, so that will be pretty large actually. And your VDD is, let's say, 1.84. FSW is 1 megahertz. So what will be your P-gate loss? P-gate switching loss. So 20 picofarad multiplied by 1.8 square multiplied by 10 power 6. How much is this? How much? 64.8. Okay, now let's say if FSW equal to 10 megahertz unit, then what would happen? Okay, so it's a direct function of your switching frequency. So now let's say you're running at 10 megahertz and you had this 100 milliohm was your loss, resistive losses in your, not resistive, but the resistance of this conduction path, where RDCR plus R1 of the devices, 100 milliohm. So how much load current should be there to have the total power of, so let's say your output voltage is 1 volt. Okay, so load current is, let's say, 1 milliamp. So 1 milliwatt you are delivering, correct? And conduction losses will be quite negligible at 1 milliamp. You can ignore that. I mean, if you compare with this loss, that will be nothing, correct? So 640 microwatt you are losing in the gate and 1 milliwatt you are delivering. So what will be the efficiency? Less than 50%. Okay. In fact, it will be 35% also. Okay. So the efficiency is too low. But if you switch at 1 megahertz, then your efficiency is boosted, like more than 90% also. So which means if your load current is reducing, and when switching losses starts dominating, we have to reduce the switching frequency to maintain high. Okay. So later, once we complete the all types of losses, I'll show the curve, which one dominates in what region. But this is just an example to tell you why really we want to go at lower frequency or switch at lower frequency when we have a light load. What could be the other way? So one way, okay, you reduce the frequency. What could be the other way to reduce this losses? Cap. We can reduce the cap. How can we reduce the cap? So we can change the size of power fed. Okay. So which means switching frequency must be reduced okay. Let's move this guy next page. Okay. Reduce here for reduce. This is called segmented field. Use smaller threads in parallel instead of single large. Okay. Turn off okay. So let's say we have 10 threads. Okay. So 10 in parallel, let's say 10 picofarad. Okay, which means one fed is 1 picofarad. So at lightest load, let's say I have only one on, so you have reduced your power consumption by 10 times. Okay, and if you reduce the frequency also by 10 times, then you get 100 times advantage in the power reduction. Okay. Another way you reduce the supply, you get a square advantage there. So let's say you reduce the supply by 3 times, you reduce the power by 9 times. Okay, but that makes your design very complicated. So usually we don't use that method. But this is a very common method used, segmented fed and scaling down the switching frequency with the load current, and that scaling down the frequency also called PFM. So pulse frequency modulation. And this is segmented fed.